Here is the second part of the presentation. Here are some approaches of rake receiver design. The first one is the most general one. The selective rake receiver just chooses the multipath components that have the largest signal-to-noise ratio, and combine them to produce the output. Oftentimes, it uses the maximal ratio combining. The simulator designed in this project is also using this combining scheme, and it was introduced previously. This combining scheme can give the largest gain in SNR. The number of multipath components is determined by the number of fingers of the receiver, and according to the different environment, the necessary fingers are different. For example, if the complexity of the receiver is strictly constrained, the number of fingers can be used may be small. But typically, 3 fingers are enough for most circumstances. The second approach is the single-path receiver, which is a special case of the selective rake. It simply chooses the component that has the largest SNR. As we can expect, the performance of this kind of receiver is worse than the previous kind, because it discards all the other components that also contain useful information, but it reduces the complexity. The third approach is all-rake receiver, which is another special case of selective rake. This kind of receivers collect all the resolvable multipath components and conduct the maximal ratio combining. That means that all the detectable useful information is used by the receiver, hence, theoretically it can give the best performance. However, it is not practical, because it has too much complexity. It may not worth to use such a receiver. Now let's see the rough analysis of these approaches. First, given a bandwidth, increasing the number of fingers can enhance the average value of SNR. That is also intuitive, because the more fingers can introduce more diversity, but as the number becomes large, the incremental gain in SNR is decreasing. The reason is that most energy is concentrated in a few multipath components, and the rest of them do not have much contribution to the performance. In fact, selective rake receivers can satisfy most requirements and can be implemented according to specific needs. Now let me draw a conclusion to part 1. First, the main work of this project is developing a simulator with a user-controlled interface, but it has some drawbacks. For example, it only uses the wash code. It does not utilize more efficient codes like gold sequence, and the pilot signal that is attached to the transmitted signal is not periodically inserted. Hence, it cannot adapt to the changes in one transmission. It can only adapt to the channel changes in different transmissions. That is to say, if the channel condition changes too fast in one transmission, the channel estimation will be degraded significantly. Those are the drawbacks that need to be improved. Finally, the experiments conducted in the simulator represents the basic idea of rake receivers, and the receiver gives acceptable performances. Additionally, by controlling the diversity of the receiver, we will see that the experimental results agree with the theoretical analysis of the 3 approaches of rake receiver. Now, let me demonstrate the simulator by giving some examples. Here is the code of the simulator. For example, we set the length of wash code to be 2 to the power of 5, that is 32. A number of users, we first set to 2 users, and set 100,000 bits per user, set SNR to 9 dB. We first see how to work with 3 fingers, then push the button get bit error rate. We will see the bit error rate this time for this decoding. And by pushing the get bandwidth efficiency, we can see the bandwidth efficiency here. In order to see the relationship between the signal to noise ratio and the bit error rate, we can plot a curve, but it will take a while to plot it. Here we can see that the bit error rate is dropping quickly as the signal to noise ratio increase. And when the signal to noise ratio increases to 10 dB, the BER drops to below 10 to minus 4. That is a relatively good performance. In order to do the comparison to other diversities, I will conduct another experiment. We set all the other parameters the same as the previous one. Here is 9 dB, but here this time we only use 2 fingers. And here again we plot the curve to do the comparison to see how diversity affects the performance. Here we can see that when the number of fingers is reduced to 2, the bit error rate to the SNR curve is changed to almost a linear one, and the bit error rate drops a little bit when the SNR increases. So the slope is flat, not as the previous one, the exponentially low. It is obviously higher than the performance where we use 3 fingers. Here are the 2 experiments conducted using the AWGN channels. Next, I will show the results of the simulation in Rayleigh fading channels. In order to save some time, I have already run the code to see the performances. Those 3 plots are conducted under the condition that the Doppler shift is 10 Hz. The first plot is using 3 fingers. We can see that although the bit error rate is large, but the slope is pretty steep. As the SNR increases, the bit error ratio drops significantly. The second one is using only 2 fingers. You can see that the slope is obviously flatter than the previous one. The third graph shows the result using only 1 finger. We can see that the performance is not acceptable in these circumstances because it is too large, and the bit error ratio is not dropping quickly. It's almost a linear one. Here is the 3 figures representing the result in the Rayleigh fading channel. Let's come to the simulator code. Here is the callback function for the get BER. when we push the button, get the bit error ratio, we will execute the following codes. First, the user information bits are randomly generated, and then they are encoded by the wash codes. Then the number of delayed chips are randomly generated and added to the different copies. Here we add AWGN to the channel. The noise is decided. The signal to noise ratio is decided by the user of the simulator. Here, this part of the code is used to decide the energy in each pilot signal. By calculating the energies in the pilot signal, we can get the weighting coefficients of each finger. And here, this part is used to represent the output, the coefficients of the receiver to the interface. Here, this is the callback function of the plot. The main method is pretty much the same with the get BER button. The only difference is that it conducts the simulation six times to get the 6 experimental points, and then at the end of this function, at the end, I use the BER fit function to fit these 6 points to a curve, to get the curve we see in the interface. Here are all the codes. Let's get back to the slides. Now that is all for my presentation for this course project. Thank you for watching, and I especially appreciate Dr. Wu for his instruction. Thank you.